In this segment, I'll show how to match up the solutions so that we have a continuous wave function and continuous first derivatives. So, previous video, we had found this solution. Again, we're focusing just on the positive part because the negative side is just can be obtained by symmetry, as we saw last time. And then, of course, the two constants k and alpha satisfy these two relationships with the energy E being negative. It's a negative number. And as usual, we require our wave function to be continuous between, so we need to match up the two solutions above and here. And also, I need to make sure that the first derivatives are continuous across this interface at x equal to a. And so those two conditions that we need to have are that psi has to be continuous. So psi from the evaluated at a from the minus side has to be equal to psi at x evaluated at a from the positive side, and likewise for the first derivatives, that they have to be continuous, and so the derivative evaluated at a from the negative from the left has to be the same as evaluated from the right. And we've got our solutions up there here. So for psi on the left side, it's just a cosine kx evaluated at x equal a minus, and that's got to be equal to psi evaluated on the right hand side of a, which is just this, evaluated from a positive. And now then evaluate these at a. Oh, I'm sorry. Then likewise the derivative, if I take the derivative of a cosine kx, I get minus a k sine kx. Derivative up here is minus a c minus alpha. And they likewise have to be continuous, and so as I evaluate them on the left and right, those have to be the same. And putting in for x on both sides, x equal to a, we then arrive at this form up here. And then let me rearrange that a little bit. For one thing, I've got the minus sign on both sides from the differentiation, so I can divide that out. And let me write that equation on top. So I get k a sine ka is equal to alpha c e to the minus alpha a. And then the top equation, I'll write that second here. And the reason is I want to divide this equation into the one above it. And so dividing this side by this one, I get ka sine kx over a cosine ka, and the a's will cancel. And the other side, I get alpha c e to the minus alpha a divided by c e to the minus alpha a on this side. And again, the c's go out, and this time the exponentials also go out. So I get this relationship that has to be solved for the energy. In the past, we were able to do this analytically, but in this case, we're not going to be able to. And so it's kind of interesting that in this one-dimensional case with a finite potential well, we can't get a closed-form analytical solution for the energy. Pretty obviously, though, I would say this, that if k is given by this square root of this expression, and alpha is given by the square root of this expression, then if I have the mass of the particle and I know how deep the potential well is, then I can plug these up here, and I've got an equation, albeit a nonlinear equation for E, that I can solve for E. So this set of equations we'll have to do some more work on, but since it's nonlinear, we have to use some numerical method, perhaps a Newton-Raphson iteration or some kind of root finding technique to find bound state energy is E that solve the equation. So, in principle, the problem can be solved, but there's no closed form solution to that box set up there. We have to use a numerical method. So we have to be satisfied now with numerical solutions and not necessarily a full analytical form for the energy E. So that's one issue. The other issue is that I can't leave A, V naught, and M ultimately as variable parameters in the problem. So to do a numerical solution of this, I have to be given what the mass of the particle is, or know what the mass of the particle is in the potential well. I have to know the depth of the potential well, and I have to know the A from the plus or minus A, that basically the width of the potential well, which is 2A in this formulation. So I have to know all of these things, and then I'll get some numerical value, knowing those specific numerical values for A, V naught, and M. I can solve this nonlinear equation up here for E and get a numerical solution for E. Well, we'll do that in the next video.